Good morning and welcome to Blue Waters webinar series. This is Maxim Belkin with the Blue Waters project at the National Center for Supercomputing Applications. And today I'm pleased to welcome you to our new webinar in the Scientific Software Ecosystems track. The title of the webinar today is Jupyter as the Interface to High Performance Computing, and will be presented by a distributed group of 3 experts. The first presenter is Matthias Bussonnier, a research facilitator at UC Merced and one of the founding members and core contributors to the Jupyter project. Our second presenter is Shreyas Cholia, a group leader in the Usable Software Systems group in the Computational Research Division at Lawrence Berkeley National Laboratory. And our third presenter today is Roland Thomas, a data architect in the Data and Analytics Services Group at NERSC. You can find brief bios of all presenters on our portal on the webinar page. As always, I'd like to remind everyone that you can post questions to presenters through YouTube chat and in our Slack channel. Information on how to join our Slack team can be found in the sidebar below. With that, I'd like to thank all of our presenters today for joining us today, and take it away.
Thank you very much. So about myself, you already said everything, so I'm going to skip that, and I'm going to directly go into a bit of history of how Jupyter came to be. Jupyter and the history of Jupyter start way before the name Jupyter appeared, and I joined about in the middle, so I'm going to go through that. Everything started in around 2001 with Fernando Perez, who was trying to slack on his PhD and decided to write some small software to help him run all his code together. And that was IPython. You might still have heard about IPython. It still exists, but that's how everything started. It was mostly to get better interactivity in the shell for doing research. Fast forward a number of years, around 2010, 2011, thanks to a grant from NSART, Fernando Perez and new people who joined the project, Brian Granger and me, Megan Kelly and others, developed something called the Qt console, which was an advance on purely a shell that can show text to actually be able to show rich displays. And here we see that in 2011, the core team of what will become the Jupyter project released what was called the Qt console. So the Qt console was something written in Qt that looked like a terminal, but when you had an object that would know how to display itself as an image or as LaTeX, it would be shown online. I arrived around this time, and in 2012, we had the first release of what you can know now as the current Jupyter notebook. At the time, it was called the IPython notebook, not yet Jupyter. And it was one of the first open source projects that was able to basically run code in a browser, communicate to a server. We'll see exactly how it works later. And that had a really huge success. And one of the key was that it was designed to not be purely for Python and had an interface where different languages could talk to it. And in 2013, the Jupyter team, which was not Jupyter team at the time yet, sat down with the folks from another language from MIT called Julia, you may have heard of now. And in about a week, we managed to get Julia to run into IPython notebook. And so in 2014, we had the question like, why do we have to install IPython if we want to run many languages like Python, Julia, or R, or other things like Haskell? And so we decided to rebrand all the parts that were not Python specific to Jupyter. And so Jupyter only exists since about 2014 as a name, but the history, as you can see, have more than a decade worth of work before that. And it's also an homage to Galileo first notebook, because now in the browser, we have those notebooks that records how we do science. And so we really like the name. And of course, there is an obvious misspelling to make it easy to Google. And so where are we in 2019? We have more than 1,000 contributors from the around 6 to 8 in 2014. So the project grew really fast. Some of the core funders gained the ACM System Software Award, which means that we really believe, some people really believe that Jupyter has an impact on science and on computing today. And there are dozens of small projects like Lego bricks that you can reuse in different aspects. And so even if people tend to think as Jupyter as one thing that you can put on use as once, you can actually reuse it in a number of different ways if you don't like the branding or how it interacts with each other. I'm going to give a few numbers. There are about 4 million notebooks on GitHub as of a couple of weeks ago. You can run the code, see how the code that try to extract that works, and modify the parameters to predict the growth of Jupyter. We have about 150 repositories, 8 million users worldwide. To give you an idea, there are about 21 million people that self-identify as developers worldwide, and 4.4 million in North America. GitHub has 24 million users, and VS Code, which is a nice ID, a nice text editor ID from Microsoft, has 2.6 million users. So we are a relatively big project. The project is made in several in different ways. We have core contributors, people that are often involved. We try to meet once or twice a year with most of the core people. You can see here some of us. Often, like some of the pictures are here in Berkeley, in California, and the other ones here is in DC. And we try to do everything as open as possible. And most of the work on Jupyter is made by volunteers. We would, of course, not be able to be such a successful project and high quality without our sponsors, that you can see some of now. And so why we created Jupyter in 2012 and the notebook, it came to our struggle with how we were working with the life cycle of a scientific idea. And we see that that was a couple of years ago, and we've updated these thoughts through the years. Circa 2012, when you wanted to do science, you would do individual exploratory work using REPL or scripts. Then you would do collaborative development using hopefully version control. Then you might want to submit that to a cluster to run things using a different kind of software. And then you would have to rewrite everything in Word or LaTeX. And then you want to educate people about what you've done, and you want to go back to the individual work. One of the issues was that you had different tools that had a lot of overhead for switching, a lot of chance for mistakes when you copy and paste. You update your code, but you forget to update your presentation, and the graph that you show to your audience is wrong. And so one of the questions is, can we make one tool that basically try to avoid that and is the only thing you can use from individual to publication to education? And that's how we decided to create Notebook. So here are some example of tools overhead. And so that's how Jupyter came to be. We created the notebook. I will discuss again after. And we have an increasing number of disciplines have a fast growing amount of data, and which it can be hard to manipulate. And we thought that technology is a tool that should empower the users, allow people from different domain and knowledge and expertise to all work together, and facilitate sharing and collaboration. And Jupyter provides, as I said, the Lego pieces that you can bring together to do that by trying to define protocols or formats. And if you don't like the default implementation, you can just replace them, but they have same defaults that are relatively approachable regardless of which domain you came from. It's openly licensed, so you can free to use it. So if you are a student on a university that can't afford a really expensive software, you can use Jupyter. But if you want to run it on HPC system and you're really advanced, you can modify it and run it as much as you want. And it's important for diversity and equal access for science to have free tools that are open source and well documented. And now we're reaching 2020, where now exploratory work is not small anymore. We now regularly have people that are using Jupyter to do exploratory work with hundreds of gigabytes of datasets, and they want to have a feedback loop in a matter of a few seconds to a few minutes, and not have to submit things on an HPC system to get the results several days later. Collaboration has also changed quite a bit. You used to email things back and forth and use Git, and now more and more people would like to have real-time collaboration and work together at the same time. We are starting to have scholarly outputs that are diverse. Like now, submitting papers that just are basically a repository of code with a DOI is now accepted as publication. We have more and more interactive figures online, and not everything is now bound to the PDF that you send to your peers. And the consumers, our output are not academia anymore. It's more and more education and the grand public. People now like to be able to see how the analyses have been done, and we're starting to see people running analysis and so on and so forth. So we've been trying to adapt Jupyter to fit some of those new goals, and that's one of the reasons we're embracing the web. So one of the things I talked about is how Jupyter came to be. I didn't really describe what Jupyter was, and it has different meaning for different people. But mainly when you hear about Jupyter, you will people think about the notebook. There are many other components, but usually that's what they mean. And the notebook is a web server, a web app that can contain code, narrative, math, and results. So that's what you have in the front end, and it's attached to a kernel doing computation. And that can be a small machine or a really big machine or a supercomputer. And the advantage of the web is that the result can be static, purely text or images, interactive, where you don't have the backend to do computation. So if you just want to pan and zoom on a graph, or it can be dynamic, which means that when you change the parameters that you can see on the screenshot there with the Lorentz attractor, it will actually completely recompute PDEs and show the result in a different way, which allow to have fast iteration over your result. You don't have to modify the code and change a parameter. You can just drag a UI element. So that's what it looks like in more detail. You have a notebook like that, where you can interleave both narrative and code. And the narrative is really important to explain what you're doing or what your results are. Because the goal of computing is not the computing itself, it's the insight that you get into your simulation or the data that you explore into the science. And for communication, it's the same. You want to be able to communicate to other people. And of course, for that, you need to be able to embed math, and you might want to have something where users can tweak parameters without having to understand the code and understand where they need to modify parameters. So the notebook is based on the WEM technology, which makes it really accessible, which means that for some people, you only need a web browser to control an HPC cluster. We haven't had people that use Jupyter on HPC system from their iPad, which I think is something I wouldn't have guessed a couple of years ago. And the web is way less scary for users, especially for new users that want to use HPC systems. They might not be familiar with the terminal and how to SSH and so on and so forth. And this is a relatively friendly interface for people to interact with that, which means that you can have domain-specific scientists that have knowledge in their domain that can interact with a really powerful system without having to learn these extra things about how to run on an HPC system. The fact that we use the web also means that we can have a rapid increase in performance and functionality. The web is ubiquitous and is evolving really fast, which means that now almost for free, as soon as browsers support new things like JavaScript just in time, suddenly our system becomes faster. We can now display 3D graph in the browser, which in a really simple manner. Now we have WebAssembly if we want to compile code inside the browser and run code inside the browser. And it's identical use for local and remote users, which means that we can both have users that are used to this application when they run from their laptop, and when they move to a lab and need to run an HPC system, they don't have to relearn something new, they just have a similar interface. And it's an interface, especially the notebook interface, which is relatively open to have multiple user collaborating. You can have people that are really good at visualization that understand how to do that, or people who are really good at writing code, of efficient code, collaborate on the same notebook, which allow to get really high quality research. The notebook is also an open document format. When you save a notebook, it's actually saved as a JSON document, which contains everything from narrative to results. It's really important to be able to have result embedded, because you want to be able to send a single file to someone, and you want them to see your result without having to rerun things, especially when it runs on an HPC system. We choose JSON to be readable from most of the programming languages. So if you want to modify a notebook or generate a notebook from another language, it's relatively easy. And we strive for simplicity so that you can write a system that can process notebooks in about an afternoon without knowing much about the internal. Because the results are embedded, there is more trust, no copy paste error, and make it easy to share. For the past 2 to 3 years, we've been working on rewriting everything from scratch in the UI to have something which is way more flexible. You may have heard it. It's called Jupyter Lab. It's completely compatible with the previous notebook that you have seen. I mean, every document you have, every research you have, every file you have can be open in Jupyter Lab, and it can even run side by side with classic notebook. It has been rethought in a better way with better frameworks and so on and so forth. So it's completely pluggable. You can bring your own custom extensions to be able to see different files that you were not able to see with classic notebook. It also gives you a more IDE-like experience where you can put panels side by side and so on and so forth, with the exception that in IDEs, I is for interactive, because we really push toward having everything interactive with live computation in the back with Jupyter Lab. And now if you start using Jupyter, I would recommend directly starting with Jupyter Lab, which gives a full features interactive environment in the browser. As I said before, you can install it side by side with classic notebooks. There is no change in file format or protocol. It works exactly the same. And all extensions are first-class citizen. You can rewrite, so change all the extension in the way that that fits your need, and with a great design. And the classic notebook will be deprecated at some point. So I can encourage you to migrate now. Jupyter also comes with many languages. You may be using it with Python, but actually a lot of people are using it with non-Python kernel. Python just comes as a default because most of it is written in Python. You can use it with Scala, with Haskell, with Julia, with Erlang. And there is also this misconception that one notebook has to be in a single language. You can actually have a single notebook with many languages that talk to each other. Not all languages are equal regarding to this point, but for example, Python, Julia, and R are relatively good at talking to each other. So it's relatively straightforward to have a notebook with Python, Julia, and R, and you can even embed some C and share objects between different languages. You need to have a good mental model of how things work. It can be quite challenging, but if you need to have both really good performance from the C side, the glue side from Python, and the visualization side from R, it's something that we see every now and then. Of course, we work on having easy and scalable deployment, especially for HPC system when you have hundreds of users. For that, we're going to use something called Jupyter Hub that allow you to have a different Jupyter server for each of your user, and it's try to hook into most of the existing single sign-on logging system. So you can just use your organization credentials and get people Jupyter on the server. And if you want to get started with that, you can go to the links below, and you can deploy a Jupyter Hub in about half an hour. It's also really useful for reproducibility. If you tweak some of the ability to start Jupyter, you can start it in a Docker container. And so now more and more, we see people publishing Git repositories on GitHub. And with a single link now, when they click on it, it will package this repository into a Docker image and spawn it for you on the cloud for free for a couple of hours. So if you want to publish a result, but you can't put hundreds of figures or want to give parameters for your user to explore, you can publish your research and user will be able to interact and see how changing the parameter of the model change the effect on your research, and basically trust that your research is reproducible and explore how changing a model can affect the result. And more what we see now are branded Jupyter deployments that are targeted towards specific use case. There is a lot of tools available, especially in the Python ecosystem, and you have to be an expert to choose which one to use. And we're starting to have things like Pangeo that say, hey, let's have an opinionated choice about the technology we use and have something targeted for climate scientists, which gives turnkey solutions to deploy really large computation system in the cloud for specific domain. And so it's using really new technology, completely managed on Kubernetes, if you heard about it, which is Docker-based. You log in via GitHub, and it persists on Google Cloud, which means that you basically have infinite scalability, automatic infinite scalability, as long as you have the money for it. I'm close to 20 minutes, so I'm going to go to a demo to show Jupyter for people who should have maybe never seen it. So let me try to exit. I've cheated and already started a Jupyter instance here. So here what you can see is what you get when you first start Jupyter Lab. What we have here is a new interface, and you see that it's way more flexible. You now have many tabs on the side here. You can browse your file system. You can start different kind of notebooks. You can even start a terminal in the browser here, which is a full-featured terminal that can even run VI or things like that on a text file. And one of the big advantage of Jupyter Lab versus a classic notebook is now many files are first-class citizen. So here, for example, I have a big CSV file. If I want to explore this CSV file without having to open a notebook, I can double-click on that, and I will just be able to see a CSV. We've thought a lot about that and make that quite efficient. So this CSV has about 1.2 million rows, and you can see that it's butter smooth if you want to explore that. And we can go to way bigger file change. You can also, for example, have a GeoJSON file. So if you have a bunch of location in a JSON file, so let me just open that. You see that it's a JSON file that has like square brackets that are relatively hard to read, but because we know it's about geographical data, if we double click on it, it will actually open it in a map, in a leaflet, and I can browse through, scroll, and so on. And one of the advantages of Jupyter Lab is you can register your own extensions if you want to see your own file in your own way. So for example, here I have a representation of a FASTA file. If you're doing biophysics, you can have directly this highlighted in a way in the way you like, or for example having a JSON graph be represented. And of course here it's running on my home computer, on my laptop, so I have only a couple of cores available. But if I wanted to run that on a supercomputer and have datasets that are gigabytes in size, that wouldn't be an issue. You could run that there. And so let me try to move to an example where I actually do some distributed computing. And so Jupyter mostly exposes an interface, and most of the power of Jupyter is that you can use most of the Python library. And it has, for example, some integration with library like Dask. If you've heard about Dask, Dask is a distributed computing scheduler, a dynamic scheduler with distributed. And so you see that here I have installed an extension that allows Jupyter to integrate with Dask, and I can see what Dask is doing. I've actually pre-populated the thing, and here I'm just going to do some data. I'm going to load an image and do some data analysis. I'm just going to run through the code. You see that it's relatively easy. I press Shift Enter when I want to start something. I'm going to load my data sets. And now I'm going to start Dask. And what Dask is doing is going to start some workers on, well, hopefully, if I'm on a supercomputer, remote nodes, and it will be able to do work stealing and automatically scale if I need to. And what you can see here is that we have direct Dask integration. So we can see on each node here, we will be able to see which task is currently being run. And the way Dask works is that when you give it some work to do, it will create a graph of all the tasks that need to be done. And then we'll go through the task one by one until the computation is complete. So what you will quickly see here is task advancing here, and you will see here a network graph with which task is being worked on, and when the last task on the right will be finished, we will have the result. That's going to be quite fast, but as you see here, Dask quickly, let me rerun that, went through all the tasks. So you can see here that I have 2 workers, and you here saw some of the computation I had to do. So calculated some of the value on my data sets. And here we see how we can bring parallelism and dynamic task scheduling and the strength of the Python ecosystem to have interactive computation at scale. We can actually run interactive computation on tens, hundreds of thousands of nodes, and that would automatically scale and give us a result. So we could work with a 100 of gigabyte or terabyte data sets. So here is me running something else. And to show you some of the interactivity here, what I'm going to ask Jupyter is to give me a UI that allow me to pick the color map. So if you don't want to have to modify the code every time and rerun it, with usually a couple of annotation, you can say, hey, I want a small UI that just give me the option to choose a color map or any other parameters you want. And now the only thing I have to do, if I'm not a guru of computing and don't understand the code, I can share that with someone who doesn't know and how to write code and say, oh, I just want to change these parameters. And now every time I click, it will recompute in the back and shows a new version of the map with those new parameters. And that's one of the strengths of Jupyter. You can have both people who are really good at writing efficient code or parallel code that's going to work with people who are domain-specific experts and just know how to explore the data and get insight into this. So I'm close to 25 minutes. So I'm going to talk about the future. The future is what you're going to build. There are many directions to go to. I can't talk about everything. We are mostly like one of the next thing we want to implement is real-time collaboration that we hope to have soon and release Jupyter Lab 1.0, hopefully in the next couple of months. And with that, I'm going to take questions while we switch speaker to Rolling, who is going to start the next presentation on NERSC and Shreyas after, I believe.
Thank you, Matthias. Just a quick reminder to our audience that you can ask questions again on YouTube and on YouTube using chat and in Slack. We don't have any questions at this moment, so let's just switch presenters.
All right, do you hear me?
Yes.
All right, great, thank you. Let's see. And bear with me, are my slides showing?
Just a sec.
All right, great. Okay, thank you.
We're ready.
Good morning. I'm Roland Thomas. I'm a data and analytics architect in the data and analytics services group here at NERSC. Shreyas is going to be talking after me. The topic of my part of the slides is going to be about what we have done to deploy Jupyter at our supercomputing center. So I'm going to talk a little bit about the motivation for why we have deployed Jupyter for users at NERSC, what some of the challenges in the deployment process have been, and what our strategy and deployment is, and some of the things that we're going to be working on in the near future here. First of all, just to introduce NERSC. NERSC is the National Energy Research Scientific computing center. We're the production user facility for the high performance computing and data for the Department of Energy's Office of Science. We're located at Lawrence Berkeley Laboratory in Berkeley, California. The building on the left houses our people and our systems. And in the picture on the right, you can see both our people and our systems. NERSC has two systems right now that it's running, two large systems. Both are Cray systems, Edison, which is going to be retired next month, is our older system, and Cori, which is our newer system. In addition to these compute systems, which have their own attached storage resources, scratch file systems, and high-speed networks, we have a NERSC global file system for users to share data between the systems and over the web. We also have network connections to the outside that are high-speed networks that allow people to move data in and out of the center. We also have a container as a service platform that is a new platform that we've been providing to users recently. It's going to figure into a lot of the infrastructure and the deployment that I'll be talking about today. Who are the people that use NERSC? We have about 7,000 users. I think on any given day, probably about 1,000 of those users log into our systems. They are spread over about 700 different projects that have funding from the Department of Energy. We help produce 2,500 plus publications per year through the use of NERSC resources. And last year we gave out 10 billion hours to those users to do their science. We have a very diverse workload. We're not a leadership class facility. That means that when users are funded by the Department of Energy and they show up with a code, our responsibility is to help them get that code working on our systems so that they can address their science issues. And we support all 6 science areas within the Office of Science. That's high energy physics, nuclear physics, materials chemistry, geophysics, fusion, plasma physics, bioenergy and environment, and of course, advanced scientific computing. And one of the main trends that we see in terms of our user presence at NERSC is an increased representation of experimental and observational data facilities. And this is really driven by advances, technological advances in the development of scientific instrumentation and detectors that allow people to ask questions that they weren't previously able to answer before and get new data rates that they are having trouble dealing with. So part of our job is to support this new experimental and observational workload, starting a few years ago and moving into the future. And for us, the challenge is figuring out how to support these new workloads alongside the simulation workload that we've been traditionally supporting, because they have different requirements. They have a very real-time need. They need to have support for dynamic workflows, and in fact, human-in-the-loop kind of analysis, or even steering of experiments that are geographically separated from the center. So part of what we've done is try to figure out how to support both the simulation and the experimental and observational data workload at the same time. Part of the mission need for the Cori system was the needs of these experimental and observational data users. So Cori is really the first system that we have deployed, which is really friendly for data users and simulation users at the same time. And we've done this through a number of different data-friendly features, including a burst buffer for I/O acceleration, a very flexible queue structure enabled by the Slurm workload manager. So shared queues, real-time queues, interactive queues are available for our users. Right away, containerization is something that we recognize is going to be really important for experiments that are running for a really long time and maybe have legacy code that they need to maintain over a long period of time and make sure runs maybe 5 years out. So we developed Shifter for containerizing high-performance computing workloads. And so Cori is the place where that was first deployed. In addition, Cori includes some special purpose extra login nodes. It has more login nodes than a usual system that we procure. In fact, I think there's about twice as many. And these are used for other purposes besides just login. They're for managing workflows, so running workflow engines, managing data, doing data transfer, using special queues for data transfer, big memory queue, and of course, Jupyter. From the beginning, one of the things we recognized was the importance of Jupyter for human in the loop kind of data analytics and exploratory data analytics. And we thought that this was going to be important, so we set aside one node for users to run Jupyter notebooks on Cori. You could take the perspective that all you need to do is provide the hardware and a way for users to SSH in, and then they could do whatever they want. And certainly they began by doing that. So users were logging in and creating SSH tunnels and then talking to Jupyter notebooks that they spawned on our login nodes. But allowing users to do that is a bit of a security concern. We need to make sure that they're running the latest and greatest version of all the packages that have all the security patches applied and things like that. So having us manage that from a centralized deployment seemed to make better sense. It's also difficult to support and manage kernels and environments for users if they're using whatever they want. So we give them a lot of flexibility. They can set up Conda environments if they're using Python that allow them to customize their user experience at NERSC, but we provide a lot of the Jupyter infrastructure for them so that we can control that and maintain it. Also, simply setting up SSH tunnels, I find that to be pretty inconvenient and pretty annoying. So Matthias mentioned Jupyter Hub. Jupyter Hub has been critical to the success of Jupyter at NERSC. That's the way that we've centralized the deployment to deploy notebooks in a standard manner that uses our authentication. We can package kernels for users so that they're ready to use Jupyter as soon as they get onto the system. They don't have a very complicated setup. If they need to get going, they simply log in and they can use Jupyter. What this does is this provides access to our resources, not just our compute resources, but our file systems, the batch queues, our high-speed network, databases that are hosted at the center. This exposes all of that through Jupyter. And so we really look at Jupyter as an important new way for our users to interact with our resources and accelerate their science. What I think is another thing that we do is when you set up a service and you maintain it for users, like our Jupyter Hub service, it really clarifies the expectations for users about what we bless and what we support for them. So I think that there's a really important communication aspect from the perspective of our center through Jupyter Hub. In some way or other, we've been working on providing Jupyter users probably now for about the last 6 years. 2014 was when the mission need for Cori was identified, and so that was sort of when we started trying to deploy IPython and Jupyter. And back then, it was simply a Science Gateway node that we had set up, which is basically just a server that was able to see the NERSC global file system. And users found that useful because they could do visualization and analytics of their data sets through that Science Gateway application. Over the next few years, we worked on ways to integrate Jupyter into Cori. As I mentioned, we set aside one login node for running Jupyter notebooks and set up the Jupyter Hub infrastructure. And at the same time, the Container as a Service platform was being stood up. And so a lot of our deployment migrated there. And we enabled Jupyter Lab, the beta, pretty early on. In fact, we made that to default just to see how that would work for users. And for the most part, it's been pretty successful. This year, we've been working on providing more compute resources for Jupyter, finding ways to extend access into the compute nodes on Cori, and creating useful extensions that make it easier to use Jupyter in HPC and at NERSC. We have a lot of feedback from our users. We do an annual user survey. These are comments from a couple of years ago. I'm not going to read all of them, but probably the most funny one, I would say, is that there are some people out there who are really fanatics about Jupyter and say that all they need is food, shelter, and Jupyter. Everything else is optional. So users really appreciate Jupyter at NERSC. They appreciate our efforts that they can run Jupyter on an HPC system. But we were having some difficulty providing stability and also the ability to scale up to the demand. What I'm showing here is a plot of the number of unique users per day who are logged into that single Cori login node. And we were averaging about 100 users on a single login node, and that's pretty high. On some days, we were spiking up to over 200, and what it turned out to be was that people were running tutorials, and they would have about 100 people all log in at the same time. This would crash the node sometimes. 30% of the time, less than 50 gig of memory was free, and so we needed to find new resources and find ways to expand to expand our ability to manage those additional resources. So that's a lot of what we do. We've been doing over the past year is try to address the demand from users for Jupyter on our system. So this slide is going to have a few animations that show how users log in and start using Jupyter at NERSC. So the big square on the outside is NERSC. The box on the right represents Cori, which has login nodes, and I've labeled there Cori 13, 14, and 19, which are the 3 login nodes that we've set aside now for using Jupyter at NERSC. So we've expanded from 1 to 3 nodes, and then another box for compute nodes. On the left, at the top is a box labeled Spin, which is our container as a service platform. So, and at the bottom, external services for supporting authentication. So when a user logs in to the Jupyter Hub at NERSC, which is jupyter.nersc.gov, they authenticate using a custom authenticator that we've written. The Jupyter Hub architecture is highly modular, and so you can adapt it to whatever your use case is if you have special needs. And in our case, authentication is something that we need to control. And so we've created our own authentication authenticator for that and plug that into Jupyter. So once the user is authenticated, they can go to either a container running in Spin or running on Cori. So this shows user connecting to Spin, which is just another container. In the Spin instance, what you can do is you can see the NERSC global file system, but you can't interact with the HPC resources. So we really see the Spin instance as something of a backup when the HPC systems are down. And if you have a paper deadline and you need to make a plot really fast, you can at least do that through the backup Spin resource. Most users, however, come to NERSC to use Jupyter on Cori, on one of those 3 login nodes that we've set aside now. We're supporting on a regular basis, I think, about 120 to 140 notebooks that are running concurrently across these 3 nodes. They can spawn their notebook over on Jupyter. Again, the spawner that we use is custom. It's a SSH-based spawner, so we SSH between Spin and Cori to launch the notebook, and then once the notebook is launched, the SSH connection goes away, and the notebook just calls back to the hub to communicate with the user. From a notebook running on one of those login nodes, we've made it possible for users to secure a job allocation that's running while they're using their notebook and communicate with a cluster, say a Dask cluster running on a compute node. All they need to know is the internal IP address of the head node of that job, and then they can make that connection, and then they can run Dask or IPy Parallel or any other kind of multi-node analysis that they want to do on a compute node from a notebook on the login node. We have another use case that we're working on delivering to users very soon, which is actually running notebooks on compute nodes. As I mentioned, there's 120 to 140 users spread across these three login nodes. That might get a little bit crowded for some users, and some users may want to use more resources than they can share with other users. So providing the ability to spawn notebooks on compute nodes is a way for them to sort of have their own compute node to run Jupyter on for a while. And to do that, we actually submit a job through Slurm. We have a software-defined networking API that allows us to hook up all of the networking that's needed. And then once that's all done, the user is connected from Jupyter Hub over to the notebook running on the compute nodes. Again, I mentioned that the Jupyter Hub architecture is highly modular. This has been a real advantage to us. We've been able to customize the pieces that we need, but also reuse and adapt pieces that have been created by other people at HPC centers who have a similar need. So in particular, the batch spawner and wrap spawner packages have been really useful for helping us to deliver Jupyter to our users. I'll just show a couple of quick slides here to show you what the hub looks like and show a couple of customizations that we've done. We manage the authentication here at NERSC. We don't have federated identity yet, but we do have multi-factor authentication. So we've customized the login page. Again, this is very trivial for us to do. Our custom authenticator puts together all the pieces that are needed for the multi-factor authentication, and that allows users to log in securely. We've also created a custom homepage running in our Jupyter installation that enables named servers. So actually users can have a link to their Jupyter server, maybe in their list of bookmarks, and they can just connect to that. And once they're authenticated, they can resume work, pick up wherever they left off. And we have here provided a way for users to select whether or not they want to run their notebook on Cori or on Spin. Okay, so all of these customizations, again, we're basically just writing Python code and adapting HTML templates. And so they're fairly straightforward. Probably the harder part is working on the infrastructure on the inside, making sure that queues are available and resources are available for users to run Jupyter on. So at that point, I'm going to hand it over to Shreyas, who's going to talk more about use cases, extensions, and customizations in NERSC.
Thanks, Roland. All right, I'm going to try sharing my screen. Hopefully this shouldn't be too complicated. Can you guys hear me okay? Or?
Yes.
Okay. And you can see my desktop. I'm going to share in a second. All right, so I've gone full screen, and you guys can see the desktop okay?
Yes.
Okay, great. So yeah, so I'm going to go a little bit deeper into the actual use cases that are running on the NERSC Jupyter system. So I lead a software group where we actually engage with a lot of a lot of scientific users who are trying to do novel things in this space, and so we help them get going. So some of the folks that we're working with right now include folks who are there's some folks who are trying to do distributed training and hyperparameter optimization. This was for the Atlas experiment where they were getting images from the detector, and they wanted to do some distributed machine learning on those images to be able to classify them. We're also working with the Advanced Light Source and the National Center for Electron Microscopy for their image processing pipeline. So they've got instruments that are taking data live and then processing those things at NERSC. So it's very useful to be able to do some real-time interactive analysis of the data that you're taking, to be able to do steering, or to be able to just get some real-time feedback on the data that you're collecting. We're also talking to some folks from the TARDIS Supernova project, and this has to do with exploration and comparison of simulation data with experimental data. So you look at supernova images and you look at spectra that are generated, and you compare that with things that are generated by simulations, and you want to be able to explore that space in an interactive manner. So what I'm going to talk a little bit more about and show you a quick movie demo is this deep learning use case with Atlas. So they've got these, they basically have a neural network set up. It's a convolutional neural network, which is great for doing image classification. And so there's a whole bunch of physics involved that I'm not going to get into, but the basic idea is that you get images from the detector and you want to run them through this neural network, and it'll tell you whether it matches a certain event, and the neural network should be able to classify those images as signal versus noise. So why this kind of interactive model? So deep learning, was all the rage, but really there's actually some merit to this. So Jupyter is really helpful in this context because in general, training some of these neural networks can take a long time. And so the whole kind of pattern of working is, you're making these choices of parameters in the neural network, and then using some combination of human intuition and brute force, you're running them through the network, seeing how things go, and then you're tweaking the parameters. That's fine, but in a kind of a batch HPC system, that's a lot of iteration, a lot of slow processing. And so what we've seen is that really in industry and in deep learning in general, there's been this convergence around using an interactive, iterative platform like Jupyter to be able to do this. And so notebooks are really popular in this community, and so it became really easy to kind of use that as one of our early use cases. So what we're doing kind of on at an architectural level, Roland already talked about this some, but this kind of we're looking under the hood a little bit over here. So you've got your Jupyter Hub web server that launches the notebook server process, and then we're using your Jupyter kernel, which then talks to something like IPyParallel or Dask, basically a framework that can talk to and communicate with a number of different workers that are running on the back end. And then we use the underlying global file systems as kind of the base that's common across all of these nodes. And so we can write out data that can be visible to all the processes. But they can also communicate with each other via MPI, and then they can communicate back to the kernel via IPyParallel. So hopefully that makes sense. You basically, yeah, think of it as a Jupyter notebook with a kernel, and then it's talking to IPyParallel to communicate with the compute nodes. So here's kind of how that works. It's a little bit of a live action movie here. So here we have a notebook that's doing this hyperparameter optimization. And what we have is a whole bunch of different parameters that you're looking through. And you want to basically just, click around and see how any one of these parameters is doing. And what you're doing is you're basically calculating the training loss and the accuracy. So you want to see if something is doing better or worse, and you can kind of look at the different models that you're running, click around through the different hyperparameters and see which particular training run is actually more successful compared to others. And what that lets you do is quickly zone in on what the actual parameter space is that's going to give you good results when it comes to training these models, which ones are more accurate, which ones have the least amount of loss. So the other thing that this also does, if you notice, there's a stop button and a restart button there. So what you can do in this case is if there's something that's just not working out and you're basically off somewhere and it's really just not a good model to be running, you can actually stop and start selected runs and tweak the parameters as you're going. So the idea here is that you actually have this very interactive way of exploring the parameter space, but you're actually using HPC resources on the back end. And what we've done here is we've built these tools using what's called IPyWidgets, and specifically there's a tool called BQplot, and there's another tool called QGrid. And what those tools are doing is they're talking to this IPyParallel mechanism on the back end, which is sending JSON over to the notebook, and the notebook is plotting these in real time as you click through the different the different options. And so we've basically glued together the front end, which is IPyWidgets, the BQplot pieces, the piece to talk to IPyParallel and just sort of render those results in a meaningful fashion. And the actual results are just coming from workers on the back end. All right, so that was our little movie talking about how we use IPyParallel to do the distributed deep learning. We've also developed some extensions. This is something that a student of mine is working on right now. We talked a little bit about using Slurm to provision things. And so it makes sense to be able to just provide support for managing your Slurm queues from within Jupyter. And so we have a little Jupyter Lab Slurm extension that can, just give you a view of what's running in the queue. It lets you launch jobs. It lets you kill selected jobs. So this is really just an interface to the various underlying Slurm commands like sbatch and sq and that sort of thing. But it provides a nice little GUI inside of Jupyter Lab to be able to manage that directly. And so moving forward, I think what we want to try and do is generalize some of this work that I just showed you with the Atlas Deep Learning use case so that any project that really wants to do some sort of parameter exploration or steering can run a job in the back end and it sends us JSON and we give you some basic widgets to plot with, and then you can have at it and do whatever you want. So we want to be able to build these tools within Jupyter Lab and build these IPy widgets to make it possible for users to manage interactive compute tasks and visualization through Jupyter. And then we want to be able to do, just have better support for parallel computing, again, in a more turnkey fashion. So you can have tools like Dask, which Matthias showed you, and then IPyParallel, which is what we were using for the previous demo. Have that be really turnkey for users, where they can just, here's the number of nodes that I want, here's the number of workers, just go ahead and get me a cluster, and here's an API to interact with it. So we want to try and make that very straightforward and turnkey. We're going to continue working on some of these extensions for Slurm and build that out a little bit. And of course, some of what's driving this is this notion of the super facility, which is where you have lots of different experimental and observational resources distributed across the globe, and you want to be able to manage workflows that involve moving data, allocating computation, running things all through the notebook. And the notebook is kind of a nice little interface to be able to do these command and control type things in a but in a very sort of modular and flexible way. So you can have a lot of control over that. And then you can, if for things that need to be codified a little bit more and just need more turnkey things, that's where Jupyter Lab comes in, and you can have full interfaces to do these things that live alongside the notebooks. And then the last thing that I wanted to quickly mention is we're working on this idea of project curated example notebooks. So these are where you have a project that has built these notebook-based workflows, and they want other people in the project to be able to just grab that and then run a copy of that notebook within NERSC. So it's similar to the Binder idea, but it's maybe a little bit more kind of constrained to a local environment like ours, where you log into our Jupyter Hub, and if you're in a project, you'll be able to see a set of notebooks that your project has curated, and then you can clone that notebook and maybe also clone some data that goes with it, clone the environment, and now you're running a private copy of that locally, but then there's some sort of a feedback loop where once you finish that up, you can check that back in. So this whole notion of curated examples and then the cloning them, that workflow is a piece that we're really interested in doing, and a lot of science users want to see that. Roland, maybe you could speak to the work on the Cray that's coming up.
Right, yeah, I just wanted to mention that we anticipate going forward that Jupyter is going to continue being one of the ways that users want to interact with our systems. And this is figured into what we're doing with the next system that we're going to be deploying in late 2020. That's the Perlmutter system here. So, in order to continue supporting the simulation, data, and learning applications, Jupyter is a very important way for doing that.
And I guess finally, Roland talked a little bit about how we'd started exposing multiple Jupyter Notebook backends, so you could launch your notebook on Cori, and then you could launch it on the Docker Spin container to have a smaller instance. But as we start to see more resources and more classes of nodes and classes of computation, really, what you want to do is be able to have users use those appropriately, and we want to give that choice to the user. So the idea is that you no longer just have a couple places where you run. Depending on your mode of operation, you could either run on this shared node on Cori or Perlmutter, or you could get exclusive access to a compute node on the back end, or you could get exclusive access to a GPU node, or you could click on this configurable button, and then you could basically define your own allocation under which you want to run the Jupyter Notebook under. And so this is really moving towards this idea of giving users a little more flexibility in terms of how to run their Jupyter instance once we have the resources provisioned. And so, in terms of the Jupyter Hub itself, as we move to this configurable model, there's a bunch of things that the user will want to be able to set. And so what Jupyter Hub needs to know and then validate is, what account can I charge to so that when I'm using these resources, they're appropriately used. Which queues can I submit to? How many nodes can they run on? How long can they run? So this is starting to look a lot like a Slurm batch script, and these are all the directives that Slurm takes. And so we want to be able to make that configurable in the context of a Jupyter queue, so you can specify all these directives in that configurable option, and then how we would do it. I think we basically need REST APIs to manage some of the backends to actually to glue all the parts together. So we're talking about, we have an existing API, but we're talking about building it out a little bit more to be able to manage things like reservations and availability. And there's pieces in place, but we have to kind of pull it all together. Roland, anything you want to add to that, or?
No, that's great.
So finally, this is all stuff that we mostly just built on work that was done in the community and tweaked it and customized it to make it work for ourselves. But we really couldn't have done this without a whole bunch of help and previous work from folks at other centers, including the Minnesota Supercomputing Institute, TAC, SDSC, and of course the Fernando and Matthias and the rest of the core Jupyter team who've built this stuff. So I think with that, we're good for questions.
Thank you very much, Reyes. And thank you actually to all presenters for a wonderful presentation. So I have a few questions for all of you. And let me start with a question related to Jupyter Notebook. So the question, I guess this is a question for Matthias. So the question is related to the choice of the file format for Jupyter Notebooks, JSON. Some people would argue that YAML would have been a better choice. In fact, I know that some organizations, they switch from Jupyter Notebooks to Markdown because when you use a notebook with a version control system, changes to notebooks are difficult for a human to parse. So do you think Jupyter Notebooks will at some point switch to YAML, or maybe have that as an option?
Well, as an option, yes, you can always create a plugin that stores things. Well, the way we store a notebook on disk, actually, they don't need to be stored on disk. That's something that people say. You can actually store it in a database. Is completely pluggable. There is a difference between the in-memory format that the application are using and the on-disk format, so you can always export and so on and so forth. Just to cut on YAML, the reason we don't use YAML is that YAML has security issues and misspecification issues. If you dive really deep into how YAML is used, you will see that different languages has slightly different way of interpreting YAML. And you have other issues like with YAML. If you, for example, have a key that has a value which is, like, for example, is just no. If you have a cell which the value would be just no, YAML would interpret that as false when it loads it, because YAMLs try to be too smart. So it is possible. The problem is we would have a lot of, we wouldn't have consistency across libraries that load and write YAMLs. And it's definitively something we explored. But so YAML, probably no, you can write it, but not by default. For Markdown, there is a specific reason. Is we thought a lot about sharing notebooks as something that does include both code, narratives, and results, which is something which is really important when you want to share with someone. You need the person to be able to see the result, because it might have taken weeks to compute on a supercomputer. And so that's one of the reasons we went for structured data with JSON instead of a purely plain text format. We have no objection on having Markdown as a way to store it, actually we discussed it, and we say like, well, can we have Markdown that stores the text and code, and have a side file that just have the outputs? We still believe that people really want to have a convenient way of having a single file you send around. But we are open to having different formats. So yes, we've seen people that have experimented with that. And if we get a lot of usage from these plugins that provide the ability to store things as Markdown, and we see that there is a great stability, there is no reason why it couldn't be included in the core as long as the core team agree and we can maintain it. Does that answer your question?
Yes, thank you very much. So my next question is related to Jupyter Hub and its use in the HPC system. So I think it's probably for Roland, but all of you are welcome to answer it, of course. So the question is, what are the advantages of having Jupyter Hub for on an HPC system for researchers working on HPC on problems that require HPC system? What do you think is like? Is there one main advantage, or other multiple advantages of having Jupyter Hub on an HPC system?
Yeah. So I'm just going to talk about Jupyter Hub because I'm going to assume that we think that running Jupyter notebooks on HPC, that there are users that want to do that, and that they have very good reasons for doing that. But the question is specifically about the choice of providing an interface to those notebooks through Jupyter Hub, which we manage for the users. I think one of the things that I brought up in the talk was that it allows us to sort of have a bit more control over which version of certain key components they're running. So as Matthias mentioned, notebooks are basically running web servers. Jupyter Lab is like running a web server, basically. So we want to be able to point users at specific installations of that we maintain and upgrade and try to keep secure. We try to respond to any kind of issues that may need to be addressed, especially with respect to getting the latest version installed for everybody, but also making sure that that's secure. So it also helps us provide better service because we know a lot more about what the users are doing. If everybody was kind of doing their own thing, we'd have to spend a lot of time up front figuring out exactly what this user has done to do their deployment of Jupyter Hub. So it gives us a little bit of standardization in that sense and helps us understand where the user might be running into problems a little bit faster, I think. But I also think that it provides users with a sense that if they're starting up a notebook by themselves through an SSH tunnel, that we're actually giving them a lot easier way to access Jupyter on our systems through Jupyter Hub, and they have a sense that we're actually supporting them.
Yeah, I think that's the part you have to keep in mind, right? If the user has to run and support these things themselves, that's time out of the researchers. When they should be focusing on their scientific problem. Instead, they're dealing with software infrastructure and building these tools, which is really something that then you have 10 researchers. All those 10 researchers are spending all their time. So you multiply that out by a factor of how many people you have there, and it's just not a good use of time for everyone to be building their own little custom version of whatever Jupyter-based tools they're doing to be able to support their science. So us standardizing that as a service really kind of helps ease the pain, make it a lot easier for people to use, and people just, all they do is log in and they have a notebook right there.
And to flip the question on its head, I'm managing also a cluster, a way smaller cluster than anything you have. Like we are not even 100 machines. Having Jupyter Hub on the cluster means that some people who don't even think they need an HPC system can use an HPC system, because you tend to have a population of people who already know how to use an HPC system say, hey, I want to use Jupyter because I like it. Now you can do the opposite. You can say people know how to use Jupyter, and suddenly you say, well, but you can use an HPC system. And suddenly they're happy because they thought that using an HPC system was something extremely complicated. And they might not be using 10 machines, but they might be running like genomics algorithm that takes weeks. And now they don't have to learn about SSH and so on and so forth. And suddenly you increase the population that can use your HPC system. And they don't even realize that they're using an HPC system.
Thank you very much for a very interesting answer. So I have actually yet another question related to this one, to the previous question. So do you have any comments on security, maintainability, and overall additional load on system administrators who have to support Jupyter Hub?
I'll go ahead and start an answer to that. Yeah, it does represent, not only does it represent a little bit of a workload on people, staff at HPC centers, but it also means that people who are trying to deliver the service need to be able to articulate the need and the motivation for Jupyter within the center to address policy questions, to address security questions. So there does need to be a little bit of understanding of how the Jupyter ecosystem works and how it interacts with the systems that are available at whatever HPC center is thinking about running. I would say that Jupyter, in terms of supporting Jupyter for users, is the kind of thing that I can do between meetings, and that includes writing code. It's basically the project where I get to write code these days. What's really nice about it is that the design is really easy to understand, and it's easy to explain to other people inside the center. So in terms of security, there's a very active set of developers who are very responsive to security issues as they've been identified. A lot of the work that's been done to secure Jupyter Hub installations has been done at HPC centers, including end-to-end SSL, which was something that was put into Jupyter Hub just late last year from some researchers at Livermore. So we continue to look at these issues, and we're going to look at these together as a group later this summer. We have a workshop for Jupyter and HPC, and so that'll be part of what we're working on and moving towards. But I would say that it isn't like you need to have 10 people working on it full time or something like that. But you can actually provide a very usable Jupyter installation to users without a really large impact on staff, I would say.
I want to point out that there is a security mailing list. I don't remember the exact, it's a Google group. We welcome you to the security mailing list. There is a private one where you just send security, like you think there's a security issue, you send that there. Some of the core developers will respond, hopefully rapidly. And there is a more open one where you can discuss security if you have questions. I want also to point out that deploying a Jupyter Hub is often more secure than letting users deploy their own, because they won't set passwords and they won't send authentication token and so on and so forth. And we're still, security on the web is extremely complicated. And I think that most people underestimate where the issues could be, and that most of the security issues would be from user executing notebook from untrusted sources that can execute code in the browser context, then security on the backend side, where the Linux permission system is relatively well working and everything. But as soon as you start to publish something in the browser from unstructured code, that's where the issue comes from.
Yeah, and in general, I think these are the kinds of things where our users are demanding this pretty heavily, and so it stops being one of those it's not about whether we can or can't do it. It's we have to find a way to support it in a way that makes sense to us. And in that context, the Jupyter Hub code base, I think, is actually quite well engineered and has security, sort of baked in. So I think it's worth doing it and doing it right, rather than letting people sort of come up with their own hacky ways of doing it.
Thank you very much. One more question. What role do you think or do you hope Jupyter will play in the future of science done on HPC systems? Do you have any plans it's it's not a secret that researchers on HPC systems they have to work with the command line. Do you think Jupyter Hub will replace that at some point?
So it doesn't have to be either or, right? So the nice thing, if you go to Jupyter Lab, you can actually click on a terminal and you have a little command line. So if you need to drop into that, it still gives you that option. I don't know, Roland, you've had some more direct interactions with people who.
I was going to say what you just said, which is that you don't have to kind of pick one or the other. That there are, there are times to use a notebook, and there are times to use to drop into a shell and do something. So you don't have to pick one or the other. I do think that there are users, in part because of I think the way that people who are coming out of higher education these days, and they're kind of used to working in notebooks and doing a lot of data analytics and data science in notebooks already. So we want to address the needs of those users. That's their workflow. We care about making sure that they're productive, and if that's the way that they're productive, then it's part of our job to figure out how the user base has already at least tried it. So I think that there's interest out there, and I think that in the long run, it's hard to say whether or not it's going to be Jupyter forever from here on out. But at least right now, we need to respond to the needs of those users and help them do their science. And so that's what the focus is.
Thank you very much. I have to apologize. We for some reason we got a black screen on our YouTube live feed at the moment. So are we good? Just give us a couple of moments. Excellent. So I'm told that we're back online. So my probably final question for today. I have actually a few more, but let me ask my final question. So what are the best ways to join a Jupyter community?
I will take that one. It's been a really challenging question. We worked on that a couple of weeks ago on our annual meeting this time in Washington. There are a lot of communication.org. You will see that there is a tab with community, and you can see that there is discourse. I would suggest to first join somewhere here if you want to ask questions or help answering questions. That would be a really nice thing. Otherwise, you're welcome to help on GitHub or on Twitter or on other mailing lists maintain, or if you want to help finding funding for Jupyter to work some of this stuff. We are open to every level. We have contributors that are really experienced developers. We also trying to work a lot on diversity and inclusion. So we have a lot of contributors for whom it's their first line of code or their first project ever. So it's really wide. It's basically what are your skills? What skills do you want to develop? And you can even contact some of us privately and ask, hey, how can I help? And we'll be happy to guide you.
I also want to point for this particular community, I think it could be useful to bring up that we are hosting a Jupyter community workshop for scientific user facilities and high performance computing. So I can post the link in the chat if that's helpful. And that's coming up in June. So if there are folks who are interested in participating, send us an email and we can, we'll be happy to have folks join.
Thank you very much, and you can send it to us as well, and we'll surely distribute it to our viewers when we send them the final reminder for a summary of the webinar. So we don't have any more questions at this point, so let's switch to the final slide. Once again, I'd like to thank all of our presenters today for a wonderful presentation. I think it was amazing. I hope that some of our viewers who are interested in joining and helping Jupyter community will do so after the webinar. Our next webinar is scheduled for May 15th and is also part of the Scientific Software Ecosystems track. It's titled Sustaining Open Source Software and Their Communities in Computational Geodynamics. With that, I'd like to thank all of our viewers for joining us today, and we'll see you again in the next webinar.